Oh, bear yourself aloft for this Module 1 of Bayesian Analysis, a bird's eye view. I'm Mark Williamson for DaCCoTA at UND. So, the purpose of this set of modules is to answer the question in as great a detail as we can, what is Bayesian analysis? So, let's get the basics down here. It is a method of assigning probability to events. A little more nuanced definition would be taking in prior beliefs, often hypotheses, and evidence, data, to generate posterior beliefs, known usually as probability. So this is a pretty common graph to show what's kind of going on. You have these prior beliefs of something, say maybe the number of birds in your backyard. You get evidence by observing, and then you synthesize the two to get your posterior beliefs about what the true nature of the thing you're observing might be. So in this example, you had a pretty low and uncertain prior belief about the number of birds, you got fairly solid evidence, and you synthesize the two to have an updated posterior belief on the number of birds. So a fundamental concept of Bayesian analysis is Bayes' theorem, where it rests on and what subsequent analyses developed from. One way to set it up is thus: the probability of a hypothesis given the data equals the probability of the data given the hypothesis, and the probability of the hypothesis over the data. So you see this here, it's Bayes' theorem, and I've explained this and how I've seen Bayesian analysis. Kind of from my point is, it's characterized as a rather intuitive theory, prior beliefs, evidence, posterior beliefs, but then a fairly complicated computation in most actual usage. And we'll get into those details as we move forward. And you can see just a little blip here. You can see all sorts of complicated graphs and steps that, Bayesian analysis can get pretty complicated on the back end. Now, another way to contrast Bayesian analysis is by explaining that it's an alternative to frequencies approaches. Frequencies, often maybe you might think of classical or standard analysis, things like p-values, test statistics, etc. Bayesian analysis is another way of doing things. And with that, you can use the Bayesian approach for most frequencies methods. So if you want to do something like a t-test or ANOVA or regression, there are Bayesian approaches to all of those. Now, one nice thing above and beyond the frequencies approach that Bayesian does is it allows you to encode expert opinion and domain-specific knowledge into the system. That's where that whole prior beliefs thing comes in. And where this is really helpful is that the predictions are a distribution of likely answers, allowing for risk assessment. So it gives you a better feel for how certain you are about a situation, which is useful if uncertainty is very important to take note of. So let's talk about the landscape we'll be exploring here for Bayesian analysis. On one end, we'll talk a little bit more about what goes into it. We'll talk about history theory, basic and detailed computational processes. On the other hand, we'll dig into examples, both basic probability, basic coding, and then more detailed. So for this first module, bird's eye view, we'll cover history theory and then basic probability. In our next module, leaves and trees, we'll do basic computation and coding. And then our deep dive, third module, will be the details. And we'll cover tests like t-tests, ANOVA, linear regression, and generalized linear models, as well as working examples in R, SAS, and even SPSS. Okay, so let's join into a little bit of history here. So the forefront of our history is Thomas Bayes himself. There he is here. You'll see his picture everywhere when you look and research Bayes. So he was an English statistician, a philosopher, and a Presbyterian minister. He was born in 1701 and died in 1761. And he attended University of Edinburgh. He had, like I said, various roles through his life, and his famous Bayes theorem was actually taken from a posthumous paper in 1763. So 1763 is a long way away from today. So what happened in interim? Well, a lot of the Bayesian interpretation of probability were developed by Pierre Simon Laplace, but after that, Bayesian analysis really wasn't commonly used until the 1950s for both philosophical and practical considerations. Continuing our history here, let's look at Bayesians versus frequentists. So what frequentist statistics consist of is the probability of events in a long term. That's what it sort of assumes towards. That's why a lot of times the coherence or reliableness of the statistics depends on the number of coin flips, time of experiments run, sample size, etc. That if you run a large number of experiments, it'll tend towards this sort of central parameter. So a big part of this is very interesting is in frequencies, parameters like mean, standard deviation, those are assumed to be fixed where the data is random. So the example here is our true parameter value, they say maybe a mean, is fixed, and then our x, or our data, is randomly distributed around it. And so how you use frequentist methods is you run to get a p-value to test probability of a test statistic given the null hypothesis. On the other hand, Bayesian analysis has different conjunction. It applies probability to statistical problems and provides updates based on evidence of new data. So this actually doesn't depend on the number of experiments. And also, very importantly, now here parameters are random while the data is fixed. So that's the flip of frequencies. So the example here is our parameters, say maybe mean, it's random, whereas our actual observations are fixed. And so that's a completely different sort of philosophy of how you approach data and analysis and all sorts of things like that. And then what you do is you run to get probability of parameter values given your observed data. So there's a lot of comparisons. Like I said, there's sort of a history of sort of animus or sort of competition between the two, where for the most part frequencies were won out until more recently, where Bayesian analysis is really ramping up. Obviously, it can be also pretty humorously contrasted, as you see to the right there. But there's a lot of ways to look at this. The most charitable and where I would fall along the line is that Bayesian and frequentist methods are different tools. They're both useful. They both have their uses. You don't have to exalt one over the other necessarily. And there's also a neutral kind of stance where you might have a reasonable preference for one and have reasonable defense of it, but you're not sort of inflamed against the other side. And of course, though, there is the spicy version where others are in fact wrong. When you have a report named "What is Bayesian statistics and why everything else is wrong," you know how you have a pretty spicy opinion. So let's take a look at the theory a little more now. So again, Bayes' theorem is at the core of it. One way of stating it in words is it updates probabilities, that is your degree of belief about something, the data, after attaining new data. So it can be set up like we've shown before, hypothesis based on data. And here's a nice pictograph where you have what goes into it. You have your prior information, your actual data, the likelihood, your theorem, and then your posterior distribution gives you your updated probability. Another way of stating it is the probability of A occurring given that B has occurred is equal to the probability that they have both occurred relative to the probability that B has occurred. And so to make this a little easier to follow, which you can replace hypothesis and data with A and B. So probability of A occurring given that B has occurred equal to probability of both occurred relative to the probability that B has occurred. So another way to think about this is sort of this conditional Venn diagram. You're looking at the probability that A has occurred given that B has occurred. So that's another way to image it. Okay, fluttering our way along to more theory, we can kind of look at some of the parts that go into it. So again, this is a very common sort of visualization. You have your prior, your likelihood, and posterior. Likelihood here being sort of analogous to your data collected. So your prior here, so that blue, it's your belief or your best guess about the data is distributed, or what is already known. Those are all ways of stating it. This might in fact be things like past experiments, past data. Whereas the data part, like I said, the likelihood function models the data. So it's values from an experiment or observation. And the likelihood is, so these two are, like I said, combined, conditional density of parameters given the data. So you generate the likelihood based on the data. And then finally we have the posterior. We have that in red here. That is the combined insight from the prior model and the observed data. So taken together, they will generate an updated belief for how the data is truly distributed. And this posterior thing, this is an iterative process. You could do this over and over again. You get new data, run this, get a posterior, use that posterior in a new analysis when you have new data as your prior, and then keep building and get better idea about things. So a great illustration of this is this graph here. I think it's great. Say you want to try and find the true probability of heads. You're flipping a coin. You hope it's 50-50, so it's like a fair coin. You start out knowing nothing. You've done no trials, so you just give it a flat probability. But then you do 2 trials and you get 2 heads. So then now this is our updated probability. It's like, well, it can't be 0 because we've gotten heads. But it could be, maybe it's a really unbalanced coin and it could be 1. But then as we go, we get more and more understanding about what the true probability is. Now here, it can't quite be 1 yet, but it might be quite high. Get up to 20 trials, it's looking pretty close to 50%, probability 0.5. 50 trials, even better. And then at 500 trials, it's really narrowing into like, that true probability can only really be found within a fairly restricted range. We've updated our belief over and over again to get a good understanding of the underlying probability. Now then, let's get our hands dirty with some examples using the Bayes theorem. So what is the probability of the patient having liver disease if they're alcoholic? So we're labeling liver disease A and alcoholic B. So here's our background information. 10% have liver disease, 5% are alcoholic, and 7 of those with liver disease are diagnosed as alcoholics. So how we could set this up here would be that, well, we see PA, that's going to be that 10% having liver disease, 0.10. Alcoholic is 0.05. PBA, that is our 0.07. So what we could do here is 0.07 times 1.05, and that is going to give us 0.14, or we could also say 14% of patients having liver disease are likely to also be alcoholic. So there we go. Let's look at another example here. Dangerous fires are rare, but smoke is common due to cooking outdoor activities. 90% of dangerous fires make smoke. So what's the probability of dangerous fire when there is smoke? So again, we have these things. I have not labeled them preemptively, so let's label them together. So dangerous fires are rare. So we want to say the probability of dangerous fire, so that's going to be A, when there is smoke, so B. So this is going to be A, this is going to be B, and then this is going to be B given A. So to pull that out, we know that that's going to be 0.01, so 1%. PB is 10%, 0.10, and then this is 0.90. 90 times 0.01, 10. That's going to be 0.09 or 9%. So 9% of dangerous fires will occur when there is smoke. All right, let's try a little more complicated example. In 4 Formula One races, Nicky won 3 while James won 1. However, it rained twice, once when James won and once when Nicky won. Question is, what is the probability of James winning the next race? So B, given the probability of A. So what we see here is we have this different information, but we have it kind of backwards. So this is our Bayes theorem, A given B, but we're actually asked to calculate B given A. So what we need to do is move it around, and really all you need to do here is essentially, move this, those will flip around to the side. That's why on this new updated equation, these are flipped around. So let's fill this out. So PA, that is going to be, actually, it's not given in percentages here, but that's going to be 50%. So the probability of rain is going to be 50%. Why? Because there was 4 races and it rained twice. So you could also put 2 out of 4. Probability of B, so that's James winning the next, James winning the race. That's going to be 0.25 because he won 1 out of 4. The probability of AB, so probability of rain given James winning, that's actually 100%, so 1 over 1, because every time James won, it rained. And so we'll plug this in here. So we have 1 times 0.25 times 0.5, which gives us 0.5 or 50%. So while he only had a 25% chance of winning normally, in the rain he has a 50% chance of winning. So there we go there. And let's wrap this up with a 4th example, which is going to be even more, have a little more work to do here. So this is the setup. There are 2 boxes. The first box has 4 red and 2 green. Second box had 4 green and 2 red. By design, the probability of selecting the first or the second box are random. So the first box has only 1/3 of a chance, while the second box has 2/3 of a chance. A box is selected at random, and a ball is selected at random from it. Okay, so you have a random box, random ball. What is the probability the ball was selected for the first box if the ball is red? So again, I have this labeled, just kind of keep things easier. A given B. So we have to fill this all out ourselves. So probability of A. So the probability of the ball is selected from the first box. So we know that the first box is chance just by itself is 1/3. So we can do that here. I'm going to do this in fractions rather than decimals because we're dealing with things that get messy. Okay, probability of B. So if the ball is red. So this is going to take more work because we have two sources of red balls, the first box and the second box. So that's actually going to be 4.6 times 1.3 plus 2.6 times 2.3. So where is this coming from here? So 4 over 6, that is the first box. That's how many balls are in there. But then the probability of selecting that box is only 1/3. Whereas the second box has 2 balls, but it has a better chance of being selected. So that's the overall probability of getting a red ball. So that is going to be 2/9 plus 2/9. We multiply those equals 4/9. So there we go. So next, we were looking at the probability to be given A. So that's going to be 4/6, because, and that's also be 2/3, because that is given that it was from the first box A here. What's the probability of a red ball? Well, that's just like if we have this here, that's known already. That's just 4 out of 6. So now we have all that here. We can finally do our calculation here. So we have 2/3 times 1/3 over 4/9. So that's going to, so you come out to, you can just trust me here, but you can pound it all through yourself to get it out. But that's going to give us 1/2 or 50%. So we have 50% chance of being from the first box if the ball drawn out was red. So let's take a look now at some real-world applications to make sure you know that I'm not just pulling your leg about this whole Bayesian being useful for stuff thing. So we can start with a general approach. So Bayesian analysis is good for any application where there's high heterogeneity or noisiness, so a lot of uncertainty with the data, especially if your applications need clear understanding of how uncertain you are. And then another useful would be when you require hierarchical models. So that's something like you have income, but that's nested within city and nested within country. So specific examples of this type of data might be e-commerce, insurance, finance, and healthcare. You can see all these might be really important, might have very messy data, and you need to be clear how uncertain you are or certain. More specific example would be Bayesian networks. So these are probabilistic graphic models using Bayesian analysis. It has a acrylic graph and a set of tables. We don't need to go into any of the details there, but just know that it's a method. This can be used a lot in natural science, like gene regulatory network, how genes interact with each other, medicine, biomonitoring, systems biology, and then just more in general data science, like classification, retrieval, processing, etc. And DataFlare here has a nice little application that they work through. And then something even more specific that's pretty near and dear to my heart here is phylogenetics. So that is going to be sort of the workhorse of tree reconstruction, trying to put together, based on information, how organisms are related to each other. Say maybe we're looking at humans and the other great apes. We want to see how the true relationship, who's closer related to who. And this method uses DNA or amino acid or even morphological characters for, say, older phylogenetics or like things that don't have DNA, like fossils. And so you start out with a prior distribution, not knowing, you put in data, and you can get the best sort of tree with the best probability. And how it works under the hood is this Markov chain Monte Carlo. We're not going to go into any detail here. That'll be left for later. But just suffice to say that it helps you hone in on the most likely probability. And a lot of times they use for methods like phylogenetics and other places. This Bayesian analysis is where you can't actually search everything. The Markov chain Monte Carlo helps you sort of get an estimate for something that you can't directly compute because it's too big. But we'll see that a little later in the third module. Okay, with that, thank you for starting your journey on Bayesian analysis with me. Very helpful if you would take an assessment here found on Qualtrics and also in the link, the descriptions below. Okay, bit of a summary and conclusion here. Bayesian analysis takes in prior beliefs and evidence to generate posterior beliefs. It's a form of hypothesis data to get a probability. So this is a philosophically and computationally different method of statistics than compared to frequentist methods. They have very different ideas about what constitutes parameters and data. So tune in next time for a more detailed look at Bayesian Analysis, Bayesian Analysis Module 2, Leaves and Trees. Here are links to all the references that I supplied. I'll also include them in the description below, so you can definitely go to these for more information about everything we've talked about here. Finally, we got acknowledgements. DaCCoTA is supported by NIH, so I'm under DaCCoTA, so if you found this information useful, helpful, please cite us. Thank you, and I'll see you next time.